Okay, 3 groups. So we have group 1, group 2, and group 3. Okay, so you guys are established group, so that's group 1. You're included too?
Yeah.
Okay, so 3, 4, 5, 6, 7, 8. Okay, we're good. That's 1 group. And then my 2 groups in here are all mumbled together. Okay, so let's do a big group. Okay, so it's not that intimidating. So you guys are gonna be group 1, all of you. And then group 2, the established group. Okay, so again, this handout is not posted on Canvas yet. You're gonna have access to it after SI, so don't worry. You're gonna have the blank version and the one that we're gonna solve. But for now, I want you guys to talk between each other to solve the following questions. But I'm gonna give you 2 minutes. Actually, no, let's do 5 minutes per question to talk with each other and then come up with an answer. If you guys need more time, you guys are gonna have to do your best guess. Okay, so again, 5 minutes per question. And then after those 5 minutes pass, one of you guys from each group, we need a group leader actually, from this group. Who wants to be the leader? Okay, you're gonna be the group leader. What about this? Who wants to be the group leader? Okay, we volunteer you as the group leader. Okay, so you guys are gonna talk with each other. You're gonna solve the question. After the 5 minutes have passed, the group leaders, if you guys got the answer, you're gonna raise your hand. Okay, and then I'm gonna choose which one is gonna tell me the answer and how you guys solved it. Okay, so we're gonna start very simple. Okay, very simple. And yeah, competition time, guys. Okay. I will post a handout afterwards. Okay, so let's start with that one, the very first one. Again, 5 minutes. Talk with each other. They're just asking for the number of signals in H&MR for that molecule that's shown in condensed formula. And actually, if we solve it before the 5 times have passed, the group leaders have to raise their hands. Whoever raises their hands first is gonna get a point. Do we have an answer?
Yeah.
Okay, everyone stop. Group 1 got the answer. So first of all, what do you think the answer is?
2 signals.
2 signals. Okay. I want one of you guys to show me how do you guys solve that and to show me the molecule in bond line. So wants to volunteer? There we go.
Yeah, right, dude.
Okay, so show us how you guys found it.
Right here, so we look at side 1 or side 2.
Mm-hmm.
Side 1. We have a signal right here, 3 hydrogens off of that carbon, that's 1 signal. And then right over here, the second signal. Right in there.
Exactly. Beautiful. Great job. Okay, so group 1 gets 1 point and we have a question. There has CH3, O, CH2. There's one more. You are correct on that one. Let's redraw this one. So it's practically the same answer at the end. They're just missing 1 carbon, so same process. Symmetry right in the middle, so we only focus on one of those planes. We have signal 1 and signal 2. It was 2. Okay, questions on that first one? We're good? Okay, group 1, you guys get 1 point. Okay. There's 2 big groups. And those of you who just joined, you're either gonna choose group 1 over here or group 2. You guys can just join in. We're doing group work. Okay, Question 2. Okay. Remember, if you guys have the answer, just raise your hand as soon as you have the answer. Talk to each other, talk to your groups. We don't know the numbers. Remember, if no one gets the answer after 5 minutes, one of you has to raise their hand and say their best guess.
What about the hydrogen?
So what you want to be the one that writes.
Yeah. Why?
We're joining either group 1 or group 2. We're doing a little competition. That's friendly, so don't worry. Final answer? Everyone stop. Okay, group 1. What's the answer?
Yes. Sorry. 7 parts per million is both.
Exactly, yeah, so why is it a multiplet? Okay, that's something that we talked about in one of the very first sessions. It's a symmetry. Yes.
Each hydrogen on the aromatic ring is for the same signal.
Exactly, yes, because remember, that's something new that we learned in Orgo 2. It's not going to be like the theoretical ones that we learned in Orgo 1. The different distances, different signals. In this case, they're all going to be clustered under one signal. And because they're part of a benzene ring, remember, you're going to have a bunch of little peaks just clustered together. So you're not going to be able to tell the actual multiplicity. So it's just a multiplet. Go for it. Yes, give me 1 second. Okay. So in this case, remember, we're looking at the hydrogen specifically in the benzene ring, right? Now, technically, we know that those 2 hydrogens would be the same signal, theoretically. The next 2 hydrogens, they're the same. And then the very last one should be the 3rd signal in the benzene ring. That's a theoretical answer. But what happens in practice in Orgo 2 is that all of those signals are going to be clustered together. So at the end, they're just going to look like one signal, and the multiplicity for hydrogens in a benzene ring, it's always going to be a multiplet. That's just a rule that we have. It's always going to be a multiplet. Yes.
How can hydrogens on this on these carbons be part of the same signal? If these are closer to here and these are closer to here.
Because on the spectrum, at the end, they're going to be all clustered together. So we know that both signals at the end are going to be around 7 to 8, right? No, because our spectrometer, it doesn't have the best resolution at the end. You might see 2 signals in the same area, but in practice,
It's all one signal.
it's just going to be one signal because they're going to be overlapping each other. So it's not going to be a clear.
Okay, so
signal.
what do you think? What would this be? Like, what would this signal? What? It would be a multiplet. So what would it? But how many like spikes?
And the multiplet is just going to be a cluster.
Oh, it's not.
There's not a specific number.
Oh,
Yeah.
Oh, okay.
Yes, there's not a specific number.
Got it. I don't know.
Okay, going back to this question. So remember, everyone, question. Because remember, single bonds constantly rotate. So once this bond rotates, the nitrogen is going to be exposed on both sides. So that's why. Question here. The ppm value, great question. So remember, that's the part that you guys have to memorize. Those are the chemical shifts for both HNMR and CNMR. Your aromatic rings are always going to be between 7 to 8. So that's how we figured out the answer for the ppm value. Question.
So regardless of how the ring looks, it's always gonna be that multiplet.
It's always
and
going to be
it's
clustered
always
together.
Gonna be the same signal. Okay.
Unless remember that he specifically tells you that you can see all of the signals. There's going to be like a parenthesis after the end of the question. Okay. He's going to specify.
Okay.
Then we distinguish those individuals.
They're all smushed together, yeah.
So let's say he had those parentheses and said you could see the individual signals, what would the answer be?
The answer should be still around 7 to 8, and then multiplicity should be 3. It's just yes, it's just a doublet.
Because that pink type.
That's the only neighbor, yes.
What makes it a multiplet? Why did you get all these random spikes?
It's a multiplet because remember, whenever we are trying to see a signal through the HNMR spectrometer, what happens is that if you don't have the highest resolution possible, some signals are not going to be really defined. So what happens with the hydrogens in the benzene ring is that at the end, you're going to have separate signals, yes, but once you print out the spectrum, it's all going to be on top of each other. It's going to be clustered together because we don't have the best resolution. If we have a really good resolution spectrometer, then yes, we can see each of those signals separate. Otherwise, no. Okay, so far, questions on that? Any other questions? We're good. Yes.
Like very close together because of like the average resonance structure with the electron density around.
No, it has to do with the actual machine, the spectrometer. If you will have the highest resolution, then we're not going to be able to separate the peaks as much.
I thought it might have something to do with like the J coupling. I'm still trying to-
It does have to do with the J coupling. So yes, you have specific values for the benzene ring, but I don't think that Wes is going to go over the J values for the benzene ring. If he does, don't worry, I will post it in the handout, okay? Okay, ready for the third question?
Now you got a point.
Yes. I forgot about the point.
Fuck, you could be the.
Okay,
Yeah.
okay.
Shannon, we're switching leader to Kayla.
We're switching leaders?
Yeah.
You're the new leader. Okay, everyone, 5 minutes. If you get the answer before then, just raise your hand.
One, here's a guy for.
Oh, we got the answer? Okay, question first.
So in lab, I know when we get like the structure and we have to figure out what it's called, or no, we get a more spectrum. We get like HMR and
Depth.
you gonna get that all or the
For this class, no, you're just gonna get HNMR and CNMR.
together.
Question. He can do it a couple of ways. He could tell you just the IUPAC name, or he could put it in condensed formula. Both forms are fair. Question. Which... Okay.
But I kind of.
Okay.
That's the reason.
Three.
Okay, 3. What do we say over here? 2.
Um,
Oh, why is it different? 3. Okay, it seems like in group 1 we didn't make one decision. Come on, people, you all have to agree. Is it 3 or 2?
Choosing choice C.
C. Everyone agrees with that. Okay, we all agree with C. What about you guys? I need one answer in specific, 2 or 3?
Wait, when did you-
2. 2. Okay, so
Two signals.
does your entire group agree?
It is two signals.
Two, one,
I don't even think if it's in the world. Two signals.
Last few seconds. Do we lock our answers?
Yes.
What about you guys? 1, 2. Everyone has to say it. 1,
Two.
2. Okay, so in this case, you both get a point. It is 2.
It's our point because they said it first.
No.
Let's be fair. Each group is gonna get 1 point for this question.
You're gonna deserve the point. Bring, you see everything so adamant.
Okay, so
Wrong answer.
it was
I thought it was 3-2. Why is it 3?
okay. So first of all, how many of you actually read the name of the molecule? Okay, good. Did we just assume that we were gonna have two methyl groups? Did we just assume that? Because remember, you have to be very specific with IUPAC. In this case, it doesn't say dimethyl. It says dichloride. So the compounds are different. If it was the dimethyl one, then yes, you guys would have been correct. But in this case, this little guy, I need one of you to show me how it looks like.
I'll do it.
Okay. And then show me the different signals that you see. Fluorine. Mhm.
Something.
Something?
Yeah, he told me to say something.
Or,
'Cause it's too quiet.
oh, okay,
Okay, so that's, that you see the drawing, is it legible?
Yeah,
yes.
That's what it's supposed to look like.
yeah, but what?
Now, show me the signals.
Okay.
Circle them.
So these two are one signal and these two are another.
Why?
Because they're like,
One cis.
so everything you can say about everything you can say about this hydrogen, you can say about this hydrogen. Same goes for these two.
Can group one give me another explanation? Mhm. Yeah. Plus, notice that overall, they're gonna be exposed to the same environment, even though they're trans to each other. Great job, thank you. So, let's draw this molecule in the chair-like view to see what we're working with. It's not a chair per se, but it has the axial positions. Either way, this is the chlorine, hydrogen, and two more hydrogens. Okay, so in this case, if we start with looking at the bottom hydrogen in here, that one is next to one chlorine and one hydrogen, and it's across from another chlorine. That's its environment. And then we check out the other hydrogen connects to the other carbon with chlorine, this little guy. That one is next to one hydrogen, one chlorine, and across from a chlorine. So overall, they're exposed to the same environment, even though there's no symmetry in the molecule. Okay, so that's why those guys are part of the same signal, and same process applies with the next two hydrogens. So any questions on this one? Yes.
So, is there any way to like, address them with like diastereotopic or antiatopic or
In this case, they technically could be. If they were distereotopic, that means that the hydrogens in here would be different, but they're part of the same signal. So they either have to be an antitopic or homotopic. One pink and one orange? These ones? Yeah, so they should be considered an name. No, it wouldn't make sense that they would be distereotopic, because remember, distereotopic means separate signals. So in any case, they should be enantiotopic. But don't worry, you're now gonna have to guess a relationship of hydrogens like that in cyclic compounds for most of the time. Okay, ready for the next question?
Always.
Always, that's good. Okay. Talk with each other. As soon as you get the answer, just raise your hand.
The number one. All the benzene hydrogens are gonna be like steadily. So I think. One, two, three, four are all.
Question? The leader has to raise their hand. The leader, everyone has to agree in the group, remember.
said
Hey,
Okay, group 2 got it first. They raised their hand first? Yes, but in this case, they evidently raised their hand first. No. Group 2 gets the point. You guys are absolutely correct. It is hydrogen number 1. Now, yes. Okay, so first of all, let's just highlight this answer. Okay, so group 2, why did we say that 1 was the answer?
the ones on the ring would be up or down. They would be away.
Mhm.
So, like one would be.
Number 1, in which area is it gonna be? In the aromatic double bond area? What's the name of the area? Aliphatic, beautiful, group 1. Aliphatic, what's the usual range for the aliphatic hydrogens? What's the usual range for aliphatic hydrogens? Okay, and let's approximate a chemical shift for this one. 2.3, beautiful.
But I thought that's not a carbonyl.
that's an ester.
It's an ester.
Okay, carbonyls and esters, where would a carbonyl be on the NMR spectrum and an ester?
Both in the heteroatom.
The carbonyl is not gonna be shown necessarily in the hydrogen, exactly. We're just looking at hydrogens.
The hydrogen on.
To an ester in the aliphatic region, like all the way to the right of the spectrum.
What about for carbonyl, like the ketone?
Ketone, same process. To the right, aliphatic.
Okay.
Because we have this carbon in between, remember, that carbon in between provides like a little cushion. So the initial effect from the carbonyl area is not as big. So that's why it's gonna be more shielded and more to the right of the spectrum.
Okay, but so even a hydrogen directly bonded to the carbon that bonded to
That would be an aldehyde? Is that what you're trying to say? Are you trying to describe an aldehyde?
Well, that's one thing, but let's say an aldehyde, and let's say the other R is also that not R.
Then it would be all the way to the left, really de-shielded, because that hydrogen is really close to that carbonyl area. That would be called an aldehyde. Ketones are gonna be in the aliphatic region for H and MR.
Maybe like a double aldehyde.
Yeah, that would be formaldehyde more specifically, but yeah. Question. Okay. Mm-hmm. Exactly, you got it. Okay, so really quickly, what's the approximate chemical shift for the molecules 2, 3, and 4? Approximate chemical shift, what is it? 7 to 8, and then very last one, number 5, approximate chemical shift.
9, 12. No, 12. For 5?
What is it?
Oh, wait, it's 12.
Ascorbic acid is not just a heteroatom, you have to be more specific with it.
Oh, we're not looking at,
For which one? This one?
for the carboxylic acid, yeah.
It's gonna be in the carboxylic acid area. It's not gonna be in the heteroatom region.
Could you rate the numbering for each?
So yeah, aliphatic was around 2.3. And let me use another color actually. 2, 3, 5, sorry, 4. Those guys are around 7 to 8. And then carboxylic acid around 10 to 12. Yeah.
2 to 4 would be the same thing.
2, 3, and 4, yes.
Got
Okay, ready for the next question. Okay. The next one is gonna get a little bit harder this time. Not people still don't know how this works. 1 point per question. Yes. I'm sorry? I'm really sorry. Can you say that one more time? Are you talking about number 5 then? The first one, this one? It's not gonna be part of the heteroatom because we're looking at the hydrogen connected to the carbon. It's not connected to a heteroatom. We only look at heteroatom hydrogens whenever they're directly connected. Otherwise, no. It provides a little cushion. Okay, everyone, get ready for the next one. It's gonna be harder this time. And a lot of words. Okay, number 45. We see some jaws on the floor.
Carbon, oh, carbon.
In this case, we're testing you on IUPAC as well.
Oh, carbon two.
Diol is.
4 more minutes, everyone.
Diol is two alcohol.
I'm sorry? Yeah, don't worry. I made some notes on that one actually. It should be there. It's on Canvas, so it should be under files and it's a folder called SI Fall 23. Mhm.
Guys, show me.
Yeah. So it's gonna give you a pretty good baseline of what your actual score might be. Mhm. But still, that doesn't mean that you should stop doing the practice problems. Still practice a lot. Group 2 got it?
7, right?
Yeah, the jury says,
The jury says 7. What about group 1?
Still working.
Still working. We need 3 more minutes before we lock our answers.
So is there a theoretical, multiplicity for the benzene hydrogens as well? If they were, they came as clearly.
Technically, yes.
We need are we expected to know that?
number 6, and then
I grew.
yeah.
2 more minutes. 2 more minutes before we lock our answers. Talk to each other, remember, everyone in the group has to agree with the same answer. One more minute.
What? Jury changes their mind, apparently.
Jury changes their mind. Don't tell me the answer yet. Don't tell me the answer yet. Okay, let's hear both. Okay, we have a 7, 15. Okay, those are completely different answers. Okay, everyone, we lock our answers, right? 15 and 7. Okay. Group 2, you guys got the point.
No way.
Yes. Great job. Okay, now, can one of you show me how you solved it? It is 15. How did we solve it?
Hey, it's done, you did, whatever. So it doesn't roll away.
Okay, so. Stuff like that. Or.
Mm. Oh, what do we see? Did we notice something, group 1?
Yeah. On the theoretical.
I did not learn. I'm on.
Roche. I don't think that he covers complex multiplicity that much, so don't worry about this problem. This should be your funsies, right? Good job, yes, amazing.
Okay, can I learn how?
Yes. So complex multiplicity is not that hard, actually. It just sounds scary, but. Okay, so first of all, how did we notice that this question was asking us for complex multiplicity instead of the normal one?
Theoretical. Alright.
Exactly, we were talking about some keywords. If you see theoretical or that the J values are not equal to each other, you're automatically thinking of complex multiplicity.
The theoretical.
Mm-hmm. So in this case, theoretical multiplicity. Okay. So for theoretical multiplicity, first of all, you have to find the signal that you're looking at. In this case, it was carbon 2, right? Okay, carbon 2 was the little hydrogen. Whoops, wrong tool. The little hydrogen over here. We're trying to find the multiplicity for that hydrogen in specific. So for complex multiplicity, I just look at the adjacent signals, and there only should be 2. So of course, we're gonna have those 3 hydrogens on top. That's how we got. Oh, sorry, yeah. I misinterpreted that. Don't worry. So that's how we got the 2 here. And then we have 4 hydrogens, right? 1, 2, 3, and 4. So that's how we got the other number. And then, yeah, you should just get 15. And actually, another clue that should have pointed to complex multiplicity is that your answer choices were given in numbers, not the actual words like singlet, doublet, those guys. So you had a couple of hints. It's theoretical multiplicity because the J values are not equal to each other. And that happens whenever we have different frequencies between the signals. But that's the concept behind it. You're not gonna have questions to ask on that. So just memorize, if you see theoretical or that the J values are not equal to each other, you have to do complex multiplicity. That's all you have to know. Yes, he does. It's usually just like one question and it's not as complex as this one. So. Okay, we practically got the other one. So that was fast. See, what do you guys think? See, since you guys said it first, yes. Group 1, you guys got it. They're gonna be distereotopic now. Why did we say distereotopic? What do we see?
Cause it's like you replace either A or B with
Show us.
something.
There you go.
If you do this one versus this one, right, and you replace this one with either like a CL, and send from here, you know, you're gonna get one that's gonna be, or the, cisgroup, the other one's gonna be transfer. So.
Those are not the correct terms.
No,
Those are not the correct
No,
terms.
that's the topic.
What do we say?
I got you, yeah.
Okay, let's give it one more try to group one.
So,
You have a song?
if you do a T test,
Yeah, you have
some
some.
things that was done was some that was like,
Mhm. Question?
Awesome.
Okay, so. So what's the terminology that we have to use instead of cis and trans? What are we finding? RNS specifically, yes.
Oh, the chirality of.
Mhm. Yes. So yes.
Yeah.
Okay, so first of all, remember that whenever you get questions like this, first thing that you're gonna look at is symmetry. First of all, do we have any symmetry in there? No, so that means that we have to jump right into the Q test. So before we do the Q test and replace anything, you have to see if you have any established characters. Where's the established character in there?
There's one on the second carbon, then. The third carbon.
Mhm. So if you at least, and you have E possible one, yes, remember the rules for distereotopic. You can either form the E and C isomers with a double bond, or if you're just looking at chiral centers, you need to establish one, and you need to form a possible chiral center, okay, which is the blue one in here. So that's why they're gonna be distereotopic to each other. Yes. Sometimes you can tell if they're in completely different environments. So that's what we saw in some of the practice problems.
And it has a possible chiral center because when you replace, let's say, HB with chlorine,
Mhm.
you have chlorine, but then you have two methyl. So then
But
why-
one methyl is connected to another chlorine.
And then what about the other?
The other methyl, it just has pure hydrogens, so they're different. So that's why that,
So let's say we replace HB with the chlorine, is it HA? And then that methyl going off the top, right, the same?
no, they're not the same. Remember that for chirality, you're gonna look at what's directly connected to each other first. So once you go left and right, yes, you just find carbons. But if you keep expanding, the one on the left is gonna have that chlorine, and the one on the right doesn't have it. So that's why it's gonna be a chiral center. Okay, ready for the next one? We're ready? Always, you two, are we ready? We're not that confident? Okay, this one I'm gonna zoom out a little bit more. In this case, you're given 3 spectra.
You split, I guess.
Yes. Okay, try to just take a picture of the answer traces, and I'm gonna zoom in into the spectra. So quickly, picture of the answer traces. We got it? Okay, let's zoom in into the ones. And actually, this is from your professor, yes. Oh, we have an answer. They got it first. They got it first. So right now we're equal. Okay, so as we can see, we didn't really have to zoom into any of those guys, but what did we notice? What did we notice?
Peak at 300,000.
Oh.
Is that the only one? Exactly, yes. We have that alcohol around 3,000. Remember the midlife crisis. And then when we're teenagers, that was the problem. That double one, it's signifying the carbonyl group. So there you go. So you didn't even need to read the H NMR or C NMR spectrum. In this case, IR was more helpful than those two. Okay. So far, questions on that one? Yes,
So the one in the rectangle, the peak by 7,200, that represents what?
a double bond, more specifically a carbonyl. So anything around 16 to 18, I think, that's when you get the double bonds. Sorry? Hmm?
Okay, yeah, so there's a carbonyl and there's an also.
Mhm. Okay, so far, any other questions on this one? Yes, you can as well. Yes, but in this case, looking at IR was faster than doing that. No, questions like that, you're not gonna get them on the exam. You're gonna get the three spectros, yes. But it's not gonna be as simple as that. For those ones, you're actually gonna have to read the HNMR and CNMR spectros.
So could you have a screen of this, like, let's say he didn't give us the IR. Could we do it on?
Of the, yeah, and actually, it should be actually pretty simple as well, just by looking at the HNMR. Because if we see in the HNMR spectrum, you have this little peak around 12 ppm. What area is that? Carboxylic acid. So as long as you remember those chemical shifts, you should be able to figure out that it should be A for that reason. So it was gonna be easier either way, if you had IR or not. That's CNMR. Sometimes, yes. Sometimes it's gonna be the three of them, so IR, HNMR, and CNMR. Sometimes just HNMR and CNMR. Sometimes HNMR, CNMR, and mass spec. Now, usually you don't need a mass spec to solve the question. Yes. No, it's gonna be mostly on HNMR. Question. The empirical formula, yeah, he's always gonna provide that. And we had a question over here. Question? Yes, it's gonna say mostly superficial. Once he starts talking about it, he's gonna go more into depth of the concepts that we talked about, but. I'm sorry? Yes, you're gonna assess it more, yes. But don't put a sad face, it's not gonna be that bad. It's not gonna be that bad.
Discuss what we're.
Mass spec. So if you compare it to what you learned in Orgo 1, it was very superficial. In this case, he's really gonna talk about it a little bit more. But once he tests it out, it's gonna be a lot different. It's gonna be mostly conceptual stuff. Like, you don't even have to worry about mass spec for Roche. Yeah, he doesn't cover it. So yeah, you're good. It's just HNMR and CNMR for you. Yes, question. The covering the regions for HNMR. Let me pull them up actually. Should be here. There you go. I'm gonna send an email with the answer key. And I have the roster now. So yes. Okay. Let's see. Okay. The next one is actually gonna take you probably more than 5 minutes. But I'm just gonna show it to you guys so you can start working on them. And then we're gonna continue with this handout, okay? So in this case, first of all, I'm gonna let you guys take a picture of that spectra. And then I'm gonna let you take a picture of the answer choices. And then answer choices, there we go.
I'm gonna.
Okay, and practically we just went through half of the questions. So we're gonna keep practicing them this Wednesday, actually. Remember, we don't have an essay session this Monday because of Labor Day, which means no class. So take advantage of that. It's gonna be a long weekend. Relax, enjoy it. But don't forget to keep doing practice problems for chapter 9, please.
So where should we do that? Like, where should we test this?
Textbook, or you just go to modules, the ones that he has posted. Okay, any last minute questions? Very good. Okay, and really quickly, let's do a little pop quiz on concept.
Wait, what's that?
Oh, okay.
Oh, you did. Oh, okay.
So actually, this part is gonna be more tailored to Wes, because we're gonna be talking about a mass spec. What's the major contributor for the N+1 peak?
Oh, bromine.
For the N+1 peak.
But the N+2?
That's the n plus two.
Okay, I feel.
That's n plus two. Nitrogen is in bold, but it's not the major contributor. What's the major contributor for the n plus one peak? Oxygen is actually under plus two. More specifically, what kind of carbon? Beautiful. Yes, carbon 13. What is the major contributor for n plus two? Whoa, whoa, whoa. N plus two, major contributor. Bromine. Second major? Chlorine. Beautiful.
Did you teach this?
Yes, last session.
Wait, what was it? I don't understand the pop. I wasn't paying attention.
Don't worry, it was still for only West students because we were talking about a mass spec. So it was like, what's the major contributor for n plus one and n plus two? And yes, we did cover it, guys. It was actually one of the very last pages of the handout. Right there. So please remember that, very important. That's gonna help you figure out a lot of the answers really quickly. He's probably gonna talk about a mass spec today, so yeah. Okay,
Repeat those two questions one more time. What was the major contributor?
what's the major contributor for the n plus one peak?
So the carbon 13.
It's gonna be carbon 13 specifically.
And then what's the second?
What's the major contributor for the n plus two peak? It's gonna be bromine. And then if I ask for the two major contributors, it's gonna be bromine and chlorine.
Okay. So that's what we need to know, like, how do we use that in practice? Or we don't?
In practice, it's gonna help you because the different ratios of the height of the n plus two peak is gonna help you determine what kind of atom you have. But you're not really gonna get asked to apply it. You just have to know the concepts.
Just need to know that.
Mhm. And then actually, last question. If I have an odd number in my n plus peak, what does that mean?
Odd number, like.
Beautiful. Okay, you guys got it. Okay, and again, actually, one more. How do I know that I'm doing complex multiplicity?
Theoretically, or different J coupling.
Beautiful, yes.
Okay, like,
Different J values.
Besides 630.
Now, what are J coupling values?
The J, okay, so if we have,
So if you get values other than, I don't need to know this probably, but if you get values other than 6 hertz, then it's probably.
so yeah, the J values are just the different distances that you have between the peaks of one signal. Whenever they're different to each other, that's when we're talking about complex multiplicity. But if they're the same, normal. Okay, any other last minute questions? Are we good?
Thank you.
Okay, we're good. Okay, I'll see you guys on Wednesday. We're gonna continue with this. What we've done so far, yes.
I'll see you on Friday, because it's the only session that works.
Don't worry, I'll see you Friday.
Question.
Yeah.
What are you gonna cover today? What do you have?
For lecture?
Yeah.
He's probably gonna cover mass spec today. Hopefully he might wrap up chapter 9, but probably not. Chapter 11? He should be starting chapter 11. I have already done the handout, so I'm waiting for him to start so we can move on.
Chapter 11, I thought you said we're gonna be covering at chapter 9.
Yeah, but on the syllabus, it says chapter 11. He had to put it there, but it's gonna be probably like crunched. So, yeah. It's your beginner files, yeah.
It's not.
I'm about to post it. Right now, when lecture starts, I'm about to post it.